Let me take you somewhere before we begin. The island of Sicily, the city of Syracuse, in the year 212 before the Common Era. It is night, and the city is dying. For 2 long years its walls have held against the armies of Rome, but tonight they have fallen, and the legions are pouring through the streets in a flood of fire and plunder. In a small courtyard, apart from the noise, an old man well past 70 is kneeling on the ground, drawing figures in a tray of sand with his finger. He is so deep in the problem in front of him that he has not noticed the city has fallen around him. A soldier bursts in, sword still wet, and orders him to rise and come. The old man asks only for a moment, not to spoil the figures he has drawn, and the soldier, understanding nothing of why a man would guard a few shapes in the dust while the world burns, runs him through. That old man is Archimedes, and we will meet him properly and understand what he had discovered when our long night brings us to him in his own time. I begin with his death only because of what it says. Here was a man who valued a diagram in the sand above his own life, and, strange as it sounds, he was not wrong too. The empire that killed him fell to ruins long ago. The shapes he was defending are still exactly as true tonight as they were then, and will still be true when nothing remains of us either. A theorem does not age, it does not fall. And that is the quiet miracle we are going to follow across 4,000 years. How a craft that began with farmers measuring mud on a riverbank became the most durable and far-seeing thing the human mind has ever made. Let me be honest with you from the very start, because we are going to pass through a great many beautiful legends tonight, and I would always rather hand you the truth, with all its wrinkles, than a smoother lie. When a story is too neat, I will tell you so. When we are not sure of something, I will say we are not sure. It costs a little of the romance, but it buys something better, which is that everything left standing at the end you can actually trust. There is nothing you need to do here, and nothing you need to keep. There will be no test, tonight or ever. If you drift off before we have left ancient Egypt, that is not a failure, that is the whole purpose. So settle in, let your body grow heavy, let your breath find its own slow pace, and let us go back now, very far back, to the banks of a great river, where every year the water rose and erased the world, and every year a few patient men knelt down in the drying mud to draw it all again. The river was the Nile, and the whole of Egyptian life was tuned to its pulse. Each summer the river swelled and spread across the fields along its banks, and for weeks the farmland of the country lay under water heavy with silt. When the flood withdrew, it left 2 things behind. It left a gift, that black, fertile mud that made Egypt one of the granaries of the ancient world. And it left a problem, because the water had dissolved every boundary line, every marker that said where one man's field ended and his neighbor's began. So each year, once the river had gone back down, the land had to be measured out afresh and the borders redrawn. Out of that yearly necessity, repeated for thousands of years, the first geometry was born. The men who did this work were called, by the Greeks who came later and admired them, the rope stretchers, because their chief instrument was a rope with knots tied at even intervals along it. With that simple tool they could measure lengths, and they could do something subtler that is harder than it sounds. They could lay out a perfect right angle on open ground, with no set square and nothing but the rope and the earth. Their trick was to make a loop knotted into 12 equal parts, and to pull it taut into a triangle whose sides ran 3 parts, 4 parts, and 5 parts. When a triangle closes with sides in exactly that ratio, the corner between the shorter 2 is always and unavoidably a perfect right angle. The rope itself forces it. And so, from a knotted cord and a piece of level ground, they raised temples and tombs whose corners were square to a precision that still astonishes surveyors today. Here's the first of my honest little cautions. We know for certain the Egyptians used the 3-4-5 relationship to make right angles. That much is documented in their own work. The neat picture of a rope tied into exactly 13 knots as their standard tool is a reasonable modern reconstruction rather than something spelled out in the surviving papyri. The essential truth is solid, though, that geometry did not begin as a set of lofty ideas, but as a manual, muddy, thoroughly practical craft in the service of fair taxes and buildings that would stand. We can say more than that, because a little of their written mathematics has survived. The most important piece is a scroll copied out by a scribe named Ahmes from an older text nearly 4,000 years ago, a long roll of papyrus filled with worked problems. From it we learn how the Egyptians handled fractions, how they found the areas of fields and the volumes of granaries, and, most beautifully, how they estimated the area of a circle. They had no notion of the number we call pi, not as we understand it, but they had a rule of thumb that worked remarkably well. To find the area of a circle, they said, take its diameter, cut away 1/9 of it, and square what remains. If you follow that recipe through, you are treating the circle as though the ratio of its circumference to its diameter were about 3 1/6, a touch too large, but astonishingly close for a working rule scratched out 4 millennia ago by men with no algebra at all. They did not know why it worked, they only knew that it did, and that was enough to fill a granary and feed a kingdom. And the Egyptians were not alone. Far to the east, between two other rivers, the Tigris and the Euphrates, in the land we call Mesopotamia, another civilization was quietly reaching even further. The Babylonians wrote by pressing a cut reed into wet clay, leaving little wedge-shaped marks, and then letting the tablet bake hard in the sun, which is a great gift to us because clay outlasts papyrus by ages, and their mathematics has come down to us in a state that Egypt's never could. The first thing to understand about the Babylonians is that they counted in a way that still governs your life, though you have probably never noticed. We count in tens, almost certainly because we have 10 fingers. The Babylonians counted in 60s. A strange choice, you might think, but 60 is a wonderfully generous number because it divides cleanly by 2, 3, 4, 5, 6, and more, which makes it a joy for splitting things into parts without awkward fractions. And that ancient base of 60 never died. It is why there are 60 seconds in a minute and 60 minutes in an hour. It is why we carve a full turn into 360 degrees, and each degree into 60 smaller parts. Every time you glance at a clock or read an angle, you are using the counting system of Babylonian scribes who have been dust for nearly 4,000 years. Their arithmetic is stitched invisibly into the way we cut up time and space. They left us 2 objects that are worth resting on. The first is a clay tablet catalogued, rather unromantically, as Plimpton 322, after the man who bought it early in the last century, and it holds a genuine shock. Ruled into neat columns and rows, it is a table of numbers, and those numbers are sets of 3 that fit exactly the relationship of the famous right triangle theorem we will come to shortly. Whole families of them, laid out in order, more than 1,000 years before the Greek whose name that theorem now carries. What the Babylonians used the table for, the experts still argue over honestly, a teaching aid, a reference for scribes, perhaps something like the seed of trigonometry. But what it proves beyond dispute is that this deep relationship of squares and triangles was known and organized in Mesopotamia long before Greece. The second Babylonian object is smaller, and to me even more moving. It is a modest round tablet on which some student, 4,000 years ago, drew a square with its 2 diagonals crossing, and wrote alongside it, in their base 60 notation, the length of that diagonal for a square of side 1, and their value is correct to a precision of about 1 part in a million. They had found, in other words, an extraordinarily accurate value for the length of a square's diagonal, the very quantity that, as we will see, would one day terrify the Greeks to their core. A schoolchild's exercise in Babylon quietly held a number that a Greek brotherhood would treat as a dangerous secret worth a man's life. But the Babylonians, practical to the bone, simply wrote it down, used it, and moved on. They wanted the answer. They did not lie awake asking whether the answer could truly exist. That difference between wanting the answer and asking whether the answer can exist is the great fault line of this whole story. And before we reach the people who fell on the far side of it, I want to carry you further around the ancient world, because geometry did not belong to the Mediterranean alone. Far to the east again, in India, priests composing manuals for the building of altars set down, in verses called the Sulba Sutras, the rules of the chord, clear statements of how to make right angles and how the square on a diagonal relates to the squares on the sides, all in the service of laying out fire altars of exact shape and area for their rituals. Here too geometry was born married to something practical and sacred, the the precise construction of an altar where a god might be met, and the Indian tradition would go on many centuries later to a triumph that the ancient world could scarcely have dreamed of. In the south of India, in what is now Kerala, a line of mathematicians beginning with a man named Madhava some 600 years ago discovered how to write certain curved and circular quantities as an unending sum, an infinite series, term after term after term, creeping ever closer to the true value without end. They found, among other things, an endless sum of simple fractions that inches step by step toward the number that governs every circle. It was an idea so far ahead of its time that Europe would not arrive at it independently for another 300 years on the road to the calculus. In a quiet corner of the world, without fanfare, the infinite had been tamed into a tidy pattern, one fraction at a time. And in China, in a great book assembled across generations and known as the 9 chapters on the mathematical art, we find whole systems of practical geometry and the solving of problems by methods of startling generality. A commentator on that book, Lu Hui, 17 centuries ago, attacked the circle in a way we will see the Greeks attack it too, by fencing it inside a many-sided polygon and steadily doubling the number of sides, drawing the straight-edged figure ever tighter against the curve. He pushed to a polygon of thousands of sides, and 2 centuries after him, Zhu Chongzi carried the labor to a place no one on earth would surpass for nearly 1,000 years, pinning the circle's ratio down to a fraction, 355 over 113. That is correct to an accuracy so fine you would need to measure a circle the width of a city to notice the error. 3 separate civilizations, none in contact with the others, all bending their minds to the same silent shapes, and all arriving at deep truths by the sheer force of patient thought. Geometry, you see, is not the property of any one people. It is something the human mind seems to find wherever it looks hard enough at the world. But all of these early geometries, for all their brilliance, the Egyptian, the Babylonian, the Indian, the Chinese, shared one deep boundary. They were, at heart, magnificent collections of things that worked. They knew that the rope made a right angle. They knew how to find an area, a volume, a diagonal. But they did not, on the whole, stop to ask why. They did not prove. They trusted their rules because the rules had never failed, because 10,000 fields and 10,000 altars had come out right. And then, on the shores of the Aegean, among the Greeks, something genuinely new happened, the birth of the single most powerful idea in the history of human thought, more powerful even than any particular discovery. Someone stopped being satisfied that a thing was true and began to demand a reason why it could not be otherwise. According to a tradition we can only half trust, the first man to do this was Thales of the city of Miletus on the coast of what is now Turkey, some 26 centuries ago. Almost everything told of him reaches us through writers who lived long after. So the details are more legend than fact, but the shape of his importance is clear enough. He is remembered as the first of the Greek sages, the first to try to explain the world by reason rather than by myth, and the first to treat geometry not merely as a set of recipes but as a body of truths that could be argued for. The loveliest story about him concerns the pyramids of Egypt, which he is said to have visited. Standing before those mountains of stone, he asked how tall they were, a question that seems hopeless, since you can neither climb a pyramid with a measuring line nor pass a rope through it. And he answered it with the shadow. He waited for the hour of the day when a man's shadow is exactly as long as the man is tall, reasoning that at that same instant the shadow of the pyramid must be exactly as long as the pyramid is high. The unreachable height on the ground became a shadow he could pace out with his own feet. Beneath the trick lies a real and profound idea, that 2 triangles of the same shape but different size keep the same proportions between their parts, so that a small triangle you can measure tells you the secrets of a giant one you cannot. It is geometry's first great gift, the power to leap from the human scale to the colossal on the strength of proportion alone. There is a second story about Thales, told by Plato himself. That I love because it is so human. One night, walking with his eyes fixed on the stars, lost in the heavens, he failed to watch the ground and tumbled into a well, and a servant girl laughed and asked how he expected to understand the sky when he could not see what lay at his own feet. From that night, Thales became the eternal image of the thinker, so absorbed in the sublime that he trips over the ordinary, and yet the ordinary and the sublime were, in his hands, the same study. The man who fell into the well was the same man who taught us that a shadow could measure a mountain. But the true revolution of Thales is quieter and harder to picture than any anecdote. He is credited with being the first to prove, to show, for instance, that any triangle drawn inside a semicircle with its long side along the diameter must have a right angle, not because it happens to in every case anyone has tried, but because it cannot fail to, by the nature of the thing. That step, from this always works to this must be so, and here is why, is the hinge on which everything turns. It is the birth of the idea that some truths can be known not by looking, not by measuring, but by pure reasoning, and known with a certainty that no amount of measuring could ever give. That idea reached its first strange flowering in a figure far more shadowy and far more fascinating than Thales, a man who founded what was at once a school, a religious order, and a secret society, and whose name everyone knows though almost nothing about him can be trusted. Pythagoras, let me be honest about him at once, because he is so famous. Of the real Pythagoras we know almost nothing. He wrote not a word, and the brotherhood he founded kept its knowledge secret and credited every discovery to the master, so that we cannot tell what he did from what his followers did. The detailed lives of him were written 700, 800, 900 years after he died, and they are thick with marvels, that he had a golden thigh, that he could be in two places at once, that he remembered his former lives. So take all of it lightly. We stand before a man who is half history and half myth. What seems reasonably firm is this. He was born on the Greek island of Samos about 25 centuries ago, and later crossed to the far side of the Greek world, to the city of Croton in the south of Italy, where he gathered around him a community bound by strict rules and a vow of secrecy, and, remarkably for that age, one that admitted women on something near equal terms. They followed odd prohibitions whose reasons are lost, refusing to eat beans, refusing to stir a fire with a knife, keeping to a vegetarian diet because they believed the soul passed from body to body after death, even into animals, so that to eat a beast might be to eat a kinsman reborn. But what makes them matter for us is their overwhelming conviction that number was the secret substance of reality. Their creed was that all is number, that the deepest truth of the universe was woven out of whole numbers and their ratios, that to understand number was to understand the harmony of the cosmos and the mind of the divine. And they had found, or believed they had found, a stunning confirmation of this faith, hidden in music. Take a taut string that sounds a note, and stop it at exactly its midpoint, so that half of it vibrates, and it sounds the same note higher, the interval we call the octave, at a length in the ratio of 2 to 1. Stop it to leave 2/3 vibrating, and you get the sweet interval of the fifth in the ratio of 3 to 2. The other pleasing intervals of music likewise answered to small whole number ratios. The most emotional and ethereal of the arts, the thing that moves us without our knowing why, turned out to hide in its heart the plainest arithmetic. To the Pythagoreans this was rapture, a proof that their creed was true. And they studied it honestly, with a single string stretched over a board, changing its length and listening, performing, without the word for it, one of the first physics experiments in history. And it is here, from this very faith that all things are whole numbers and their ratios, that catastrophe came. For when they turned their own celebrated theorem upon the simplest figure imaginable, they opened a hole in the floor of their world. The theorem that in a right triangle the square on the longest side equals the sum of the squares on the other two is worth stating plainly here, because it is the pivot of the disaster. Now take the humblest square, a square whose side is one single unit, and draw the diagonal across it. That diagonal is the long side of a right triangle whose two short sides are each of length 1, so the square upon it must equal 1 plus 1, which is 2. The diagonal is therefore a length which, multiplied by itself, gives exactly 2. And the Pythagoreans proved, this is the blow, that no ratio of whole numbers, however large, can be that length. There is no fraction whose square is 2. The side of the square and its diagonal have no common measure at all, There is no unit, however fine you make it, that fits a whole number of times into both. Sit with how strange this is. Two lines lie in front of you, the side and the diagonal, both perfectly real, both easily drawn, and yet the relationship between them cannot be captured by any whole number or fraction that has ever existed or ever will. The diagonal slips out of the numbers entirely. It is a quantity of a different and more troubling kind, one whose decimal expansion runs on forever without repeating and without pattern, what we now call an irrational number, from the word that means simply not a ratio, though the name also carries the flavor of the scandal it caused, of something that seemed to defy reason itself. For a brotherhood whose entire faith rested on all is number, this was not a mere puzzle. It was a crack in the foundation of the world. If the simplest square held within it a length that was not a number in their sense, then the cosmos was not, after all, built purely of the whole numbers and their harmonies they had worshipped. And there is a dark legend attached, that a member of the order named Hippasus let this terrible secret out and was drowned at sea for it. I have to tell you, in keeping with my promise, that this is almost certainly a later invention. The historians who have weighed it treat the drowning as a story that grew in the telling. What is accepted is only that the incommensurable was discovered, and that it caused a genuine crisis in Greek thought, but like the tale of Archimedes and his circles. The legend carries a truth the facts alone would miss, that this discovery really was an earthquake, and that there is something fitting in imagining a man punished for revealing that, at the heart of the simplest shape, hides the endless and the unspeakable. Now, most tellings of geometry leave the crisis there as a shudder and a shrug, but the Greeks did not shrug. They did something magnificent with it, and the man who did it is one of the most important mathematicians almost no one has heard of. His name was Eudoxus, and he found a way to reason rigorously about these unruly lengths without pretending they were ordinary numbers at all. His idea, which took genius to see, was to compare magnitudes not by measuring them, but by testing them against every possible whole number ratio at once, to say that two lengths stand in the same proportion as two others, if, whenever you try to trap them with any fraction you like, they fall on the same side of it, every single time. It sounds abstract, and it is, but it is also exactly right, so right that when mathematicians finally put the whole of number on a firm footing more than 2,000 years later, in the 19th century, they found themselves reaching, almost word for the idea of Eudoxus. He had healed the wound the irrationals opened, and he had done it with an elegance that outlasted empires. Eudoxus gave the Greeks something else, too, a method that reaches forward across the centuries toward the calculus itself. To find the area of a shape with curved sides, he taught, you fill it up from the inside with straight-edged figures whose areas you can find, a few of them, then more still, each batch fitting the curve more snugly and leaving less and less uncovered, until the gap you have failed to fill can be made smaller than any amount you care to name. You never quite reach the curve in a finite number of steps, but you corner its area between what you have covered and what remains, tighter and tighter, without end. This patient squeezing of a curve between the straight things you understand is one of the deepest ideas humanity has ever had, and it is the seed from which, 2,000 years later, the whole machinery of the calculus would grow. It was Eudoxus who planted it, quietly, to deal with lengths that would not behave. And since we have touched the idea of a process that goes on without end, forever approaching but never arriving, I must bring in the strangest and most delicious troublemaker of the ancient world, a man named Zeno, who used exactly that idea to try to prove that motion itself is impossible. Zeno posed puzzles, and they have refused to die for 2,500 years. The most famous imagines a race between swift Achilles and a plodding tortoise, in which the tortoise is given a head start. Before Achilles can catch the tortoise, said Zeno, he must first reach the spot where the tortoise began, but by the time he arrives there, the tortoise has crawled a little further on. So Achilles must now reach that new spot, and again, in the time it takes him, the tortoise has moved a little further still. Each time Achilles reaches where the tortoise was, the tortoise has inched ahead, and so, Zeno argued, the fastest runner can never overtake the slowest crawler, because there are infinitely many gaps to close, one after another, without end. We know, of course, that Achilles wins the race. You can watch a fast thing overtake a slow thing any afternoon. So where is the flaw? The answer is one of the most beautiful reconciliations in all of thought, and it hinges on the very idea Eudoxus was circling. Those infinitely many gaps that Achilles must cross are each smaller than the last, and they shrink so quickly that their endless sum is not infinite at all, but adds up to a perfectly ordinary, finite distance, crossed in a perfectly ordinary, finite time. An unending series of pieces can have a finite total. That single insight that you can add up infinitely many things and get something finite is one of the pillars the modern world stands on, and Zeno, by insisting it was impossible, forced humanity to understand at last why it is not. He is the friend who is most useful when he is most wrong, the man who mapped a chasm by daring us to prove it could be crossed. Before we leave this founding age and come to the man who gathered all of Greek geometry into a single perfect edifice, there is one more inheritance from the early Greeks that shaped mathematics for 2,000 years. 3 innocent-sounding challenges that would haunt geometers until almost our own time. The Greeks loved to build figures using only 2 tools, both idealized to perfection, a straightedge for drawing lines and a compass for drawing circles, and nothing else, no marking of measurements, no cheating. With those 2 instruments they could do a great deal, and they set themselves 3 problems that looked, at first, as though they must surely yield to enough cleverness. The first was to square the circle, to construct, with straightedge and compass alone, a square whose area exactly equals that of a given circle. The second was to double the cube, given a cube, to construct the side of a second cube with exactly twice the volume. This one carried a legend that the people of Delos, ravaged by a plague, were told by an oracle that to be spared they must double the size of a certain cubical altar, and that, taking the oracle too literally and doubling each side, they only made the altar 8 times as large, and the plague raged on, until in despair they turned to the geometers. The third problem was to trisect the angle, to cut any given angle into 3 exactly equal parts with those same 2 tools. For more than 2,000 years, the finest minds threw themselves at these 3 problems and failed, and along the way discovered wonderful things in the failing. One early Greek, Hippocrates of Chios, not the physician, a different man while chasing the squaring of the circle, managed to find certain crescent-shaped regions, bounded by 2 arcs whose areas he could turn exactly into squares. These lunes were a tantalizing partial victory. He had squared a piece of curved figure, and it seemed for a moment that the full circle must be within reach. It was not. And the deepest thing about all 3 problems is how their story ended, which I will only foreshadow now and complete when our night reaches the modern age. They ended not with a solution, but with a proof that no solution exists, that these constructions are not merely hard, but forever impossible, forbidden by the very nature of the tools. And the proof of that impossibility, when it finally came more than 2 millennia later, would not come from geometry at all, but from a new and unforeseen understanding of number, one that reached back and settled the ancient questions from a direction the Greeks could never have imagined. The oldest problems in the science would be closed by ideas their askers could not have dreamed. But that lies far ahead of us tonight. For now we are still in the bright morning of Greek mathematics, and it is time to meet the man who built the house that all the rest of geometry would live in for the next 2,000 years. That man was Euclid, and he worked in Alexandria, the city Alexander the Great had founded on the edge of Egypt, which had grown into the greatest gathering of learning the world had yet seen, with a library that meant to hold every book in existence. Of Euclid's own life we know almost nothing, not the year of his birth, nor his birthplace, nor his face. He survives entirely in a single book, and the book is enough. It is called simply The Elements, and it is, without exaggeration, one of the most important objects our species has ever produced. Let me give you its measure. After the Bible, The Elements is the book that has gone through the most editions in the whole history of print. For more than 2,000 years, from its writing until barely a century ago, it was the geometry textbook of the human race, studied almost unchanged, generation after generation, across every civilization that inherited it. Lincoln, as a grown man riding the law circuit, is said to have carried a copy and worked through its proofs by candlelight to teach himself what it meant to reason with rigor. The philosopher Spinoza wrote his entire ethics in its form, with definitions and axioms and proven propositions, as though morality itself could be built like geometry. A young Einstein was handed it as a boy and never forgot the shock of it, the sensation of touching something certain. Few books have shaped so many minds so deeply for so long. And here's the strange thing. Euclid did not discover most of what is in his book. Thales and Pythagoras and Eudoxus and dozens of others had found the results already. What Euclid did was rarer and, in the end, more powerful than any single discovery. He organized. He took the whole sprawling inheritance of Greek geometry and built it into one flawless logical structure, in which nothing is assumed without being stated, and everything else is forced to follow. He began with a handful of definitions, and a short list of plain starting assumptions he called postulates, that between any 2 points you can draw a straight line, that any line can be extended, that you can draw a circle with any center and radius, that all right angles are equal. And from those few grains, and nothing more, he deduced, in an unbroken chain, hundreds of theorems, each one leaning only on what had already been proven, with no gap and no appeal to the eye. This is the axiomatic method, and it is one of the supreme inventions of the mind, the discovery that from a few things granted, pure logic can compel a whole world of certain truth, needing no experiment, no measurement, no faith. Let me show you a single jewel from inside that structure, so you can feel what Greek proof is like, because it is one of the most beautiful arguments ever made, and it can be followed lying in the dark with your eyes closed. Euclid asked whether the prime numbers, those numbers like 2 and 3 and 5 and 7, that cannot be split into smaller factors, the indivisible atoms of arithmetic, ever run out. As you count higher, primes grow rarer, and you might well suspect that somewhere far out along the number line the last one appears, and after it there are none. Euclid proved there is no last prime, and he did it without ever finding a single large one. Suppose, he said, that the primes did run out, so that you could gather every prime that exists into one finite list. Now multiply them all together, every prime there is, and then add one to the result. This new number, whatever it is, either is itself a prime larger than any on your list, or it can be divided by some prime, but it cannot be divided evenly by any prime on your list, because you built it to leave a remainder of exactly one every time. So, either way, there must exist a prime you did not have. Your complete list was not complete. And since this trap springs no matter what finite list you start with, the primes cannot be finite, they march on forever. Notice that he has proven something about all the infinitely many numbers there will ever be, with certainty, in a few sentences, without checking even one case. That is the power Euclid gave the world, and once you have tasted it, you understand why the Greeks thought geometry was the nearest thing to touching the eternal. 2 stories cling to Euclid, both probably invented, both perfectly true to his spirit. In the first, a king of Egypt, finding the elements heavy going, asked whether there was not some shorter, easier road to geometry, fit for a busy monarch, and Euclid answered that there is no royal road to geometry. No shortcut, not even for a king. The path must be walked step by step, and neither power nor wealth can buy a pass. In the second, a student, having learned the very first proposition, asked what he would gain by all this, what it was good for, and Euclid, in cold contempt, told a servant to give the boy a coin, since he must needs profit from what he learns, and then dismissed him. To Euclid, to ask what geometry was good for was to have missed the whole point. It was to be studied for its own sake, for the beauty of its truths and the pure joy of understanding. And the deep irony, which the whole rest of our night will keep proving, is that this knowledge, pursued for no use at all, would turn out, again and again, to be the exact key the world would one day need. There is one more thing to note about the foundation Euclid laid, and I will only point at it now and leave it, because it becomes the great turning of our entire story much later. Among his handful of starting assumptions, 4 are short and instantly agreeable, the kind you nod at. But the 5th is long and awkward and far less obvious than the rest, a statement about lines that never meet however far they run. It sits in the foundation like a stone that does not quite fit, and for 2,000 years it would nag at everyone who studied him, and the attempt to remove it would eventually crack the whole idea of space wide open. But that is a door we will not open until the proper hour. Remember only that it is there, waiting, while Euclid was ordering all of geometry in Alexandria. The man who would push the subject further than anyone else in the ancient world was living in that same Syracuse where our night began, and it is time, at last, to properly meet Archimedes. He is reckoned by many the greatest mind of antiquity, and one of the few mathematicians of any age fit to stand beside Newton. He wrote to the scholars of Alexandria as equals and friends, and his mind held two gifts that almost never share a single skull: the purest, most abstract genius for proof, and the most practical cunning of an engineer. He built the war machines that held Rome off Syracuse for 2 years, screws that lift water and are turning in fields to this day, systems of pulleys with which, it was said, he could move a loaded ship single-handed. Yet he thought his machines mere distractions, and his mathematics the only thing in him worth remembering. The result he loved above all others, the one he asked to have carved on his tomb, was about a sphere and a cylinder. Imagine a ball fitted snugly inside a can, a cylinder just tall enough and just wide enough to hold it, touching top, bottom, and sides. Archimedes proved that the ball fills exactly 2/3 of the can, 2/3 of its volume, and, just as neatly, 2/3 of its surface. That perfect, simple fraction, wrung out of the roundest and the straightest of solids, seemed to him so beautiful that he wanted it, and not his engines of war, to mark where he lay. And there is an epilogue that is one of the most moving moments in all of science. Within a couple of generations his tomb was lost, overgrown and forgotten, until a Roman official arrived in Sicily who happened to revere him, Cicero, the great orator, and set out to find it. No one could tell him where it was. Some said it was gone. But searching among the brambles of a neglected graveyard, Cicero found a small pillar half swallowed by weeds, and carved upon it, worn but unmistakable, a sphere within a cylinder. He had found the grave of the greatest of the Greeks, recognized not by a name or a list of victories, but by a theorem, remembered, across the centuries, by the elegance of a single truth about a ball in a can. Archimedes also gave us a principle you have felt every time you lowered yourself into a bath and grown lighter, and every time you have watched a heavy ship sit calmly on the water instead of sinking like the iron it is made of. He understood that a body plunged into a fluid is buoyed up by a force equal to the weight of the fluid it shoves aside, the principle of buoyancy, which is truly his and truly one of the pillars of physics. There is, of course, the famous story that he grasped it in the bath and ran naked through Syracuse shouting that he had found it, having realized he could test whether a king's crown was pure gold by the water it displaced. I have to tell you the tale is almost certainly a later ornament. Its earliest source wrote 2 centuries after his death, and the crude water-spilling method it describes would be far too imprecise to catch a goldsmith's fraud. The great Galileo, long after, pointed out that Archimedes surely used a subtler and far more sensitive method, weighing the crown while it hung submerged. The principle is real and immortal, the naked dash is decoration, and he understood the lever, that humblest and most magical of machines, by which a small push far from the pivot can lift an enormous weight close to it. He grasped its law so completely that a saying was hung on him: "Give me a place to stand, and I will move the earth," meaning that with a long enough lever and something to rest it on, no weight in the universe, not the world itself, would be beyond a single hand. Whether he ever said the words, they capture exactly his sense of what mathematics is, a way for the small human mind to take hold of the colossal. 2 of his stranger achievements deserve a place tonight because they show a mind reaching past its age. In one short work, he set out to count how many grains of sand it would take to fill the entire universe. Not to be silly, but to defeat a lazy idea of his day, that some quantities are simply too large to be numbered at all. The Greek way of writing numbers gave out long before you reached such sizes, so Archimedes first built a whole new system for naming enormous numbers, and then, having the language for it, calmly estimated the grains needed to pack the cosmos full. He was making a quiet and radical point that no number is beyond reckoning, that the finite mind can name and handle magnitudes it can never see. And in another work, lost for most of history and only recovered in our own time, he revealed the secret of how he really made his discoveries. That book, called The Method, had been scraped off its parchment in the Middle Ages and written over with prayers, its geometry buried beneath religion for 700 years, until modern scholars, peering through the later ink, read the ghost of Archimedes underneath. And what they found was astonishing. He had discovered his results by imagining his shapes sliced into infinitely many thin pieces and weighing them, in his mind, against one another on an imaginary balance, reasoning with the infinitely small in a way that would not become respectable mathematics for another 1900 years, when the calculus at last caught up with him. He had the idea and hid it, using it only in private to find his theorems and then proving them properly, the rigorous Greek way, once he knew the answer. The greatest mathematician of the ancient world kept a secret method that was, in truth, a rough draft of the modern one. A third great geometer completes the golden age of Greek shape. Less famous than the others, but earning the title his contemporaries gave him, the great geometer. His name was Apollonius, and he devoted himself to a single family of curves that would, more than any other, turn out to be written into the fabric of the heavens, though no one alive could have guessed it then. Picture a cone, an ice cream cone, or better a double cone, two cones joined tip to tip. Now slice through it cleanly with a flat cut, and look at the edge the cut reveals. If you slice straight across, you get a circle. Tilt the cut a little, and the circle stretches into a closed oval, an ellipse. Tilt it further until the cut runs parallel to the slope of the cone, and the curve springs open and never closes again, running off to infinity, a parabola. Tilt it further still, so that it slices through both cones at once, and you get a pair of separate sweeping branches, a hyperbola. 4 curves, 1 cone, differing only in the angle of a single cut. Apollonius studied these conic sections with a depth no one would match for centuries, and gave them the very names we still use. In his own time, they were the purest of abstractions, a magnificent game with no earthly use anyone could name. Hold them in mind as beautiful and useless. Our night will come back for them, far from here, and put them into the sky. There was, in that same Alexandria, a librarian of such wide curiosity that he earned a gentle nickname among his colleagues, meaning that he was second best at everything and first at nothing, which was unfair, because he did one thing no one before him had done at all. His name was Eratosthenes, and he measured the size of the whole earth without leaving Egypt, using a shadow, a well, and a clear mind. He had learned that in a town to the south, far up the Nile, on the longest day of the year, the noon sun stood so perfectly overhead that it lit the very bottom of the deep wells, and a vertical stick cast no shadow at all. But he knew that on that same day, at that same hour, in Alexandria to the north, an upright stick did cast a shadow. The sun there stood a little off from straight overhead. On a flat earth, the sun's rays would strike both towns at the same angle. That they struck at different angles could only mean the ground curved between the two places. He measured the shadow's angle at Alexandria and found it to be about a 50th of a full turn. So the stretch of ground from the southern town to Alexandria had to be about a 50th of the whole way around the earth. He knew that distance, he multiplied it by 50, and out came the circumference of the planet, a figure that, depending on exactly how we translate his ancient units, lands within a few % of the truth. He never sailed around the world. He sat still, thought hard, and deduced the size of the entire globe from 2 shadows and a length of road. It is perhaps the purest demonstration ever given of geometry's strangest power, to know the unreachable by pure reason. And this is the moment to bury a myth that will not stop being repeated, that people once believed the earth was flat, and only learned otherwise with Columbus or the great voyages. It is simply false. Educated Greeks had known for centuries that the earth is a sphere, and known it by elegant argument. They saw that in an eclipse of the moon the shadow the earth throws is always round, and only a ball casts a round shadow in every direction. They saw that as you travel north or south the stars overhead change, which makes sense only on a curved surface. They saw ships sink hull first below the horizon, mast last, as though dropping behind a bulge of water. The roundness of the earth was settled knowledge, and Eratosthenes did not merely assume it, he weighed the very sphere. The Greeks gave geometry one more great branch before their long day ended, and it grew out of the need to map the sky. To predict the wandering of the planets and the turning of the stars, the astronomers needed a way to calculate the sides and angles of triangles from partial knowledge, a way to turn an angle into a length and back. This is trigonometry, and it began with an astronomer named Hipparchus, who built the first tables relating angles to the lengths of the chords they cut across a circle so that the heavens could be reduced to arithmetic. Centuries later, in Alexandria, Ptolemy gathered all this astronomy into a vast and magisterial book, so authoritative that it came down to later ages under a name given it by Arabic scholars, the Almagest, the greatest. In it he perfected the tables of chords and laid out a model of the cosmos with the earth motionless at the center and everything wheeling around it on a clockwork of circles turning upon circles. That model was wrong, as we now know, and yet it was a triumph of geometry, for it fit the observed sky so closely that it reigned unchallenged for 1400 years. Whatever else it was proof that the tangled dance of the planets could be captured in shapes and numbers, that even the heavens obeyed geometry. The trigonometry Hipparchus and Ptolemy forged to chart a mistaken cosmos is the same trigonometry that now guides ships, aims bridges, and lets the phone in your hand know where on the round earth it is standing. But the great age was closing. Alexandria's day was fading, its library dwindling through fire and neglect and the long indifference of centuries, and the last brilliant light of ancient mathematics burned in a woman. Her name was Hypatia, and she was a mathematician, an astronomer, and a philosopher of such standing that students came from across the Mediterranean to hear her, and letters survive begging for her guidance. She wrote commentaries that helped carry the works of the earlier masters forward, including the conics of Apollonius and Ptolemy's astronomy, polishing and preserving the inheritance so that it might survive the gathering dark. She lived, though, in a city torn by faction and fear, and she was caught in its hatreds. One day a mob seized her in the street and killed her with horrifying cruelty. Her death has come to stand, fairly or not, as the symbol of an ending, of the closing of the long Greek morning, of learning going quiet around the shores of the Mediterranean, of a library and a way of thinking guttering out. And in honesty, the truth is more tangled than the symbol. Her murder was as much about the vicious politics of her city as about any war on knowledge, and the decline of ancient science was slow and had many causes. But something real did end with her. For a long stretch after, in the lands that had been the heart of Greek learning, the lamp of geometry burned very low. It did not go out. But to find where it was carried and kept alive, and where it blazed up again into something new, we have to follow it eastward and south, to another civilization entirely, one that would not only save the treasure but add to it, and that is where our night goes next. While the old Mediterranean learning lay dormant, a new civilization gathered up the torch and carried it further than anyone before. From Baghdad in the east to Cordoba in the far Spanish west, the Islamic world entered a long golden age of scholarship, and among its first great labors was translation. Scholars sought out the works of the Greeks, Euclid, Archimedes, Apollonius, Ptolemy, and rendered them into Arabic, studying them, correcting them, keeping them alive through centuries when they might otherwise have crumbled to nothing. A great many of the ancient texts we possess today survive only because someone in that world copied them into Arabic, from which, ages later, they were turned into Latin and given back to a Europe that had nearly lost them altogether. Without that long act of stewardship, half of what we have been speaking of tonight would simply be gone. But these scholars were never mere caretakers. They took the inheritance and grew it, and in one direction they created something the Greeks had never quite possessed, a whole new way of handling the unknown. In Baghdad, some 1200 years ago, a scholar named Al-Khwarizmi wrote a book on the solving of equations, on how to find an unknown quantity by balancing what you know against what you seek, moving terms from one side to the other, restoring and comparing until the hidden number stands revealed. From the Arabic word in his title for this restoring, al-jabr, comes our word algebra, and from his own name, worn down through Latin over the centuries, comes another word you use without thinking, Algorithm, a step-by-step procedure that grinds reliably to an answer. Here is a man so influential that two of the plainest words in mathematics are his fingerprints. And what matters for our night is that his algebra was not divorced from geometry, but wedded to it. To justify his methods for solving equations, Al-Khwarizmi drew pictures. He showed that solving a certain kind of equation is the very same act as completing a square, literally filling in the missing corner of a square figure to make it whole. The unknown was a length, its square was an area, and to solve for it was to complete a shape. Algebra and geometry, which we are taught to think of as separate subjects, were, in his hands, two views of a single thing, a marriage that a European we will meet later would celebrate again, and that has never since been dissolved. The Islamic world also gave us a figure I find irresistible, because he united things we imagine can never live in one person. The most delicate poetry and the deepest mathematics. His name was Omar Khayyam, and he lived some 900 years ago in Persia. In the West, he is famous chiefly as a poet, the author of short, wistful, sensual verses about wine and love and the swift passing of a life which became beloved the world over. But this same man was a first-rate astronomer who helped reform the calendar into one more accurate than the one much of the world used for centuries after, and a mathematician who did something genuinely new with the curves of Apollonius. There are equations, called cubics, that involve an unknown multiplied by itself 3 times, problems of volume rather than area, and the algebra of Khayyam's age could not crack them by formula. So Khayyam reached instead for geometry. He found that if you draw the right conic sections, the right parabola, the right circle, and let them cross, the point where they intersect marks the solution to the cubic. He was using the abstract curves that Apollonius had studied, for their own sake, 13 centuries earlier. As instruments to solve problems no one in Apollonius's day even knew how to ask. And more remarkable still, he sensed that some of these problems could never be solved by straightedge and compass alone. An intuition that pointed, dimly, straight at those ancient impossible constructions, and that would not be proven right for another 700 years. A poet who wrote about the shortness of life, quietly opening a door that would take 7 centuries to walk through. The astronomers of that world reshaped trigonometry as well, turning Ptolemy's clumsy tables of chords into the cleaner idea of the sine, and adding the tangent and its companions, building the tools into the form students still learn today. They needed this precision for a very concrete and daily purpose, to determine, from any city in a vast empire, the exact direction of the sacred city of Mecca, so that the faithful could turn to pray. To point true across the curved surface of the earth is a problem in the geometry of the sphere, and in solving it for the whole reach of their world. They carried spherical trigonometry to a height the Greeks had never reached. Faith, once again, drew out mathematics, exactly as the flooding of the Nile and the building of altars had before. And there is one more gift from that civilization, and it is one you can see with your eyes rather than follow with your reason. Because their sacred art turned away from depicting living figures, the artists poured their whole genius into pattern, into covering walls and ceilings and floors with geometric shapes that locked together perfectly, leaving no gap and no overlap, repeating and interlacing in designs of hypnotic intricacy. This is the art of tessellation, of tiling the plane, and it reached a summit in places like the Palace of the Alhambra in Granada, whose halls are a kind of silent treatise on symmetry made of colored tile and carved plaster, patterns unfolding in every direction as if toward infinity. There is a deep mathematics hidden in these designs, the study of exactly how many fundamentally different ways a pattern can repeat across a flat surface. A question with a precise and surprising answer that mathematicians would not pin down until the 19th century, and which belongs to a story we will come to when symmetry itself takes center stage later tonight. I will only plant here, with an honest caution, 2 things. The often repeated claim that the Alhambra's craftsmen used every single one of those possible symmetries is disputed among careful scholars who count fewer, and the truth of exactly how many is genuinely unsettled. But a stranger and better founded discovery is that certain Islamic tilings, made centuries ago in places like Isfahan, achieve patterns that never exactly repeat. However far you extend them, the same astonishing property that a Western mathematician would rediscover, to great fame, only in the 1970s, and that turned out to describe a form of matter no one knew existed until it won a Nobel Prize in our own time. Craftsmen following their sense of beauty had walked, by hand and eye, into one of the subtlest corners of modern geometry, 500 years early. When this treasure at last flowed back into Europe through the translators of places like Toledo, where Arabic works were turned into Latin, and through merchants who carried the elegant new numerals of India and Arabia across the Mediterranean to replace the clumsy numerals of Rome, the continent was waking from its long sleep. And as it woke, in the bright workshops of the Italian Renaissance, geometry was reborn in a place no one expected, not in the study of the philosopher, but on the easel of the painter. For the artists of that age were seized by a problem that is, underneath, one of the deepest in all of geometry: how to paint the round, deep, three-dimensional world convincingly onto a flat panel, how to make a corridor recede, a floor of square tiles march away into the distance, a building sit solidly in space, all on a surface with no depth at all. The breakthrough is credited to an architect named Brunelleschi, who around 600 years ago is said to have staged a startling demonstration in Florence. He painted a small, exact picture of the city's baptistery as seen from a particular spot and bored a little hole through the panel. You were to hold the painting up with its back to your eye, look through the hole from behind, and hold a mirror at arm's length in front so that you saw the painted image reflected. Then, whisking the mirror away, you saw the real building behind it. And the painted baptistery and the real one matched so perfectly, edge for edge, that the eye could not tell which was which. He had cracked the rules by which the three-dimensional world projects itself onto a flat surface and made a picture obey them exactly. A colleague, Alberti, soon wrote the method down, teaching painters to imagine the canvas as a window or a fine veil, through which they looked at the scene, tracing onto the glass exactly where each ray from the world to the eye passed through. And a third figure, Piero della Francesca, was that rare being, a great painter who was also a serious mathematician, and who wrote treatises turning the painter's craft into rigorous geometry, and who studied the perfect solids so lovingly that his own face was later borrowed to portray a philosopher in a famous painting of them. At the heart of what these painters discovered lies a single idea so strange and so beautiful that it would grow, in time, into a whole new geometry. It is the vanishing point. Look down a long straight road, or a set of railway tracks, or the rows of tiles on a receding floor, and you see the parallel lines appear to draw together and meet at a single point far off on the horizon. In the real world, those lines never meet. That is what parallel means. But to the eye, and on the canvas, they do meet, at a definite point. The painters, to make their pictures true, had to treat that meeting point as real, and to draw their parallel lines converging upon it. And in doing so they were, without quite knowing it, adding something to geometry that Euclid had never allowed, a place where parallel lines meet, a point at infinity. The horizon became a line made entirely of such points, one for every direction in which you might gaze. What began as a trick to fool the eye was the first glimpse of a space larger and stranger than the one Euclid described. Within 2 centuries, a few mathematicians seized on this and built it into a new branch of the subject, called projective geometry, the geometry not of measurement but of appearance and projection, of how shapes look when cast, like shadows, from one surface onto another. Its founder was a French engineer named Descartes, an eccentric and difficult man whose work was so far ahead of its time and written in such a thicket of odd private vocabulary that it was neglected and nearly lost for 200 years. In this new geometry, the awkward exceptions of the old one melted away. Parallel lines no longer needed a special rule. They simply met, like all other lines, at their point at infinity. The 4 separate curves of Apollonius, circle, ellipse, parabola, hyperbola, were revealed to be, in this larger view, a single kind of thing seen from different angles, each one the shadow of a circle cast in a different way, one curve wearing 4 disguises. Descartes proved a lovely theorem about 2 triangles that are, as a painter would say, in perspective from a point, cast from a single eye, showing that certain points determined by them must always fall on one straight line, a fact about shadow and projection that measurement alone would never suspect. A boy of 16 read Descartes and caught fire. His name was Blaise Pascal, and he would grow into one of the towering minds of the age, a mathematician, a physicist, and finally a religious writer of piercing depth. But as a teenager he proved a theorem of such elegance that it still bears the flavor of a magic trick. Take any 6 points on one of those conic curves and join them in order into a lopsided hexagon. Now extend the pairs of opposite sides until they cross. Pascal proved that the 3 crossing points so found always lie, no matter how you scattered your 6 points on the curve, upon a single straight line. There is no reason the eye can see for this to be true, and yet it cannot fail. He called it, with a young man's flair, his mystic hexagram, and from that one theorem he is said to have drawn hundreds of further results, all tumbling out of a single hidden order in the conics. But projective geometry, like so much in our story, was discovered before its time, admired by a few, and then largely forgotten for 100 years and more, until it was revived, astonishingly, in a prison. In the bitter Russian winter, as the shattered remains of Napoleon's grand army retreated from Moscow, a young French officer and engineer named Poncelet was left for dead on the field, taken prisoner, and marched off to a bleak captivity on the banks of the Volga. He had no books, no instruments, nothing to do through the long cold months but think. And so, from memory, out of what he had learned as a student, he rebuilt the whole of geometry in his mind and pushed it forward, laying the foundations of modern projective geometry on scraps of paper in a prison camp, warming himself at the fire of pure thought while the snow came down outside. When he was freed and came home, he wrote it all up, and the subject he had reconstructed in captivity became one of the great fields of the 19th century. Among the jewels he brought back was a principle of haunting symmetry, called duality, that in this geometry, points and lines are perfect mirror images of each other, so that any true statement about points and the lines through them remains true if you simply swap the words point and line throughout, every theorem secretly carrying a twin, its reflection, true for free. It was as though the subject had a hidden symmetry built into its grammar, a rhyme between two things we had always thought entirely different, and that idea that geometry might be governed by hidden symmetries is one we will see grow, later tonight, into something that reorganizes the whole of the subject. But first we must return to that marriage of algebra and geometry that all Khwarizmi had begun, and watch it consummated by a philosopher lying in bed, watching a fly. His name was Descartes, and he is one of the founders of modern thought, the man of the famous line, "I think, therefore I am." He lived 400 years ago, and he was hungry above all for certainty, for a method that could reach truths as solid as those of geometry in every field it touched, and in a short appendix to a larger philosophical work, published in the year 1637, he set down an idea so simple and so far-reaching that it changed what mathematics could be. Here is what he saw. Any point on a flat surface can be pinned down completely by just 2 numbers. Think of the floor of a room. To name a spot on it exactly, you need only say how far it lies from one wall and how far from a second wall meeting the first at a corner. 2 distances, and the point is fixed with no ambiguity at all. Descartes proposed drawing 2 lines across the plane, crossing at a right angle at a chosen origin, the axes, and letting every point be labeled by its 2 distances from them, its coordinates. It is the very system by which a map's grid names a town, or a game of battleship names a square. And the moment you have it, something marvelous happens. Every curve becomes an equation, and every equation becomes a curve. A circle is no longer only a shape you draw with a compass. It is the set of all points whose 2 numbers satisfy a certain simple relation, and that relation can be written down and worked upon with the tools of algebra. A line, a parabola, any curve at all becomes a statement about numbers, which you can manipulate by pure calculation, without drawing a thing, and any such statement about numbers can be made visible as a shape. This is the marriage Al-Khwarizmi had begun, and Descartes now sealed forever, the union of the world of figures with the world of numbers, so that a problem too hard to see could be solved by calculation, and a calculation too abstract to grasp could be understood by drawing it. Two subjects that had lived apart for 2,000 years, cultivated by different people and different languages, turned out to be a single subject written in two scripts, and Descartes taught us to translate freely between them. We call this analytic geometry, and it lies under nearly everything that came after. There is a charming story that the idea came to him as he lay in bed one morning, watching a fly wander across the tiled ceiling and realizing he could pin down its position at any instant by counting tiles across and tiles up. It is a lovely image, and probably invented, and I mention it only because it captures the essence so well. A whole new mathematics born from the simple thought that a point is just two numbers. Justice demands that a second name be spoken here, for at very nearly the same moment, and entirely on his own, another Frenchman reached the same idea and in some respects carried it further. He was Pierre de Fermat, a quiet magistrate who did mathematics for love in his spare hours, and who scattered some of the deepest ideas in the subject through his letters and the margins of his books. Fermat and Descartes had prickly, competitive dealings, and the coordinate plane bears Descartes' name alone by the accident of fame, but the discovery was truly shared. It is one more instance of a pattern we will see grow almost eerie as the night goes on, that great ideas, when their hour has come, tend to arrive in more than one mind at once, as though they were ripe and waiting in the air of the age. And what this marriage of shape and number opened, within a single lifetime, was the most powerful mathematical instrument ever forged. Once a curve was an equation, you could ask precise questions about how it changes, how steeply it rises at each point, how much area it sweeps out, and answer them by calculation. From that grew the calculus, the mathematics of continuous change, discovered in the same few years by two rival giants, the Englishman Isaac Newton and the German Gottfried Leibniz, who arrived at it independently and then quarreled bitterly through their followers over who had come first, in one of the ugliest priority disputes in the history of science. We now credit them both, and the calculus, for all its later machinery, is at bottom the fulfillment of that ancient dream we met long ago on the Greek shore, the dream of cornering a curved, changing thing by an endless sequence of straight, simple ones, the infinitely small at last made into a reliable tool rather than a private trick. What Eudoxus had planted and Archimedes had used in secret, the 17th century brought fully into the light, and with it humanity gained the power to describe the fall of a stone, the swing of a planet, the flow of heat, the spread of a wave, to write the changing world itself as mathematics. And all of it rests on Descartes' small, strange thought that a point is only a pair of numbers. Let me turn now, while the night is still deepening, to a shape so perfect that the ancient Greeks thought it belonged to the gods, and to a truth about it that is one of the most surprising in all of geometry. Because here, logic sets an absolute limit that no cleverness can pass. We have spoken of regular figures in the flat plane, but lift your mind now into 3 dimensions and ask for the most perfect solids possible, bodies whose every face is the same regular shape, whose every edge is the same length, whose every corner is identical to every other, so symmetric that no part can be told from any other part. How many such flawless solids can exist? You might guess there are many, an endless family growing ever rounder. There are 5, only 5, in the whole of space, forever, and we can see exactly why. There is the tetrahedron, 4 triangles meeting to a point like a little pyramid. The cube, 6 square faces, the honest die. The octahedron, 8 triangles, like 2 pyramids glued base to base. The dodecahedron, 12 5-sided faces, a shape of almost unsettling beauty. And the icosahedron, 20 triangles, the roundest of them, a faceted near ball. And that is the entire list. Not 5 so far, with more perhaps awaiting some future genius. 5, provably with a 6th forbidden by the nature of space itself. The reason is so clean you can hold it whole in your mind. To build a corner in 3 dimensions, at least 3 faces must come together there, and the flat angles they bring to that corner must add up to less than a full turn. Because if they summed to a full turn exactly, they would lie flat, spread out on a table, and make no corner at all. There has to be something left over for the shape to fold up out of the plane. Now try each regular tile in turn. The triangle's corner is 60 degrees, so you can gather 3 of them at a point, or 4, or 5, and still have room to fold, and those are your tetrahedron, octahedron, and icosahedron, but 6 triangles make a full flat turn and cannot fold, so the triangle gives exactly 3 solids and no more. The square's corner is 90 degrees. 3 squares fold into the cube, but 4 lie flat, so the square gives 1. The pentagon's corner is 108 degrees. 3 fold into the dodecahedron, but a 4th overshoots the full turn, so the pentagon gives 1. And the hexagon's corner is 120 degrees. 3 of them already make a full flat turn, folding into nothing at all, so the hexagon, and every shape beyond it, gives none. 3 from the triangle, 1 from the square, 1 from the pentagon, 5, and the door closes. There is something moving in a fact so absolute. It owes nothing to us, nothing to our world or our minds. Any thinking creature anywhere in the universe, pondering perfect solids, would arrive at exactly these 5 and no others. It is the kind of truth that has made people suspect mathematics is discovered rather than invented, that these 5 shapes were somehow already there, waiting before there was anyone to find them, and will still be there when everyone is gone. Plato loved these solids so fiercely that his name is stamped on them still, and he wove them into a vision of the cosmos, matching 4 of them to the 4 elements the ancients believed the world was made of: sharp-pointed tetrahedra for fire, stable cubes for earth, and the others for air and water, and reserving the 5th, the 12-fold dodecahedron, for the shape of the heavens themselves. It was wrong, of course. Matter is not built of little perfect solids. But the intuition beneath it, that the universe is written in the language of geometry, would prove, in ways Plato could never have dreamed, astonishingly right. And no one felt that intuition more passionately or was more gloriously misled by it than a man who lived 2,000 years after Plato and stood at the very hinge between the old dream and the new science. His name was Johannes Kepler, and he is one of the most human figures in all of astronomy. Brilliant, mystical, tormented, and honest to the bone. As a young man, Kepler was seized by a single ravishing idea. There were, in his day, 6 known planets, and so there were 5 gaps between their orbits, and there were, as we have just seen, exactly 5 perfect solids. Surely, he thought, this could be no coincidence. Surely God had built the cosmos by nesting those 5 solids one inside another, each snug between 2 planetary spheres, so that the sizes of the orbits were fixed by the perfect shapes packed between them. He worked it out in loving detail and published it with joy, a universe held together by the 5 Platonic solids. A crystalline set of Chinese boxes with a planet riding on each shell. It is one of the most beautiful wrong ideas in the history of science, and Kepler cherished it to the end of his life, even as his own later discoveries dissolved it. Because Kepler was, above his mysticism, a man who would not lie to the data. He came into possession of the most precise observations of the planets ever made. Decades of painstaking measurements of the position of Mars, and he set himself to fit Mars's path to a circle, for everyone, from Plato to Ptolemy to Copernicus, had taken it as unquestionable that the heavens must move in perfect circles, the noblest of shapes. He labored for years. He got maddeningly close, but the best circle he could draw missed the real Mars by a tiny amount. An error smaller than the width of a thumbnail held at arm's length, and where a lesser man would have shrugged it off as measurement error, Kepler refused. That small, stubborn gap between the circle and the truth tormented him, and in the end he did the thing that took real greatness. He let go of the circle, the shape everyone had trusted for 2,000 years, and asked what curve Mars actually traced. And the answer was an ellipse, one of the very curves that Apollonius had sliced from a cone 18 centuries before, purely for its abstract beauty, with no notion that it was anything at all. Here, at last, is the payoff I promised you when we left those curves in the Greek dark. The planets do not ride on circles. They sweep along ellipses. The sun sitting not at the center, but off to one side, at a special point of the oval. The useless curves of Apollonius turned out to be the very tracks along which the worlds move. The heavens were geometry after all, only not the geometry anyone had guessed. Kepler is worth one more moment because he asked another question so homely you would never expect it to matter. and it turned into a puzzle that outlasted him by 4 centuries, helping to consider how cannonballs might be most tightly stacked in a ship's hold. He wondered what is the densest possible way to pack spheres, balls of equal size, into a space. Anyone who has seen oranges piled at a market knows the answer by instinct. You lay a flat layer in a staggered grid. Then nestle the next layer into the hollows, and the next into the hollows of that, and so on. Kepler declared that this familiar greengrocer's stack is the tightest arrangement there can be, that no cleverer packing could ever squeeze the balls closer. It seems obvious. It is fiendishly hard to prove, because you must rule out every possible arrangement, including wild, irregular ones no grocer would ever try. Kepler's guess stood unproven for nearly 400 years, one of the most stubborn open problems in mathematics, until it was finally settled at the very end of the 20th century by a proof so vast and so dependent on computers grinding through mountains of cases that mathematicians needed years just to satisfy themselves it was sound. Sometimes the deepest difficulty hides inside the most ordinary sight. A pile of fruit on a stall, guarding a secret it takes 4 centuries and a machine to unlock. The final word on the moving heavens belongs to Isaac Newton, who took Kepler's hard-won ellipses and revealed the reason beneath them. Kepler had found what the planets do. Newton found why. He proposed that a single force, gravity, reaches between every 2 bodies in the universe, pulling them together, and he proved, with the new calculus and with the old geometry of the conic sections, that any object moving freely under such a force must trace one of exactly Apollonius's curves. A planet, bound to the sun, sweeps out an ellipse. A comet, flung in from the cold and swinging once around the sun to be lost forever, rides a parabola or a hyperbola, one of the open, escaping curves. Throw a stone, and its arc through the air is a small piece of one of these same curves. The entire vault of motion, from a tossed pebble to a wandering comet, is written in the 4 curves a Greek once cut from a cone for no reason but their beauty. That is the deepest lesson our night keeps teaching, and it will teach it once more astonishingly than ever, before we are done, that knowledge sought for its own sake, with no use in view, has a way of becoming, generations later, the exact key the universe was waiting to be opened with. But now we must return to a single loose stone in Euclid's foundation, the awkward 5th assumption I asked you to remember and leave, because the 2,000-year struggle to dislodge it is about to crack the very idea of space itself. Recall that Euclid built his whole vast edifice on a handful of starting assumptions, and that 4 of them are so plain you accept them without a flicker, a line between 2 points, a circle of any size, and so on. The 5th is different. It is long and clumsy where the others are short and clean, and it makes a claim about the far reaches of the plane that no one can ever check by looking. In the form later writers gave it to make it clearer, it says, take a straight line, and a point somewhere off to the side of it, then through that point there runs exactly one straight line that never meets the first, however far you extend them both, one and only one line parallel to the given one. Not none, not many. Exactly one. Read it, and it sounds fair enough, but it does not feel like the others. It feels less like a bedrock assumption and more like a theorem in disguise, something that ought to be provable from the 4 simple truths rather than granted for free. And that feeling gnawed at mathematicians for 2,000 years. For 20 centuries, the finest geometers of every civilization tried to prove the 5th assumption from the other 4. To pull that awkward stone out of the foundation and show it was really a beam resting on the rest. The Greeks tried, the scholars of the Islamic Golden Age tried, the Europeans of the Renaissance and after tried. They produced proof after proof, and every one, without exception, was found to contain a hidden flaw of exactly the same kind somewhere in the argument without noticing. The author had quietly assumed something that turned out to be just the 5th assumption wearing a different coat. They kept proving it by secretly using it, like a man trying to lift himself off the ground by pulling on his own belt. The postulate would not be dislodged, but neither could anyone quite believe it might be false, for it described space exactly as everyone saw it. It was a thorn that geometry could neither pull out nor push in. One man in the 18th century, an Italian priest named Saccheri, came within a breath of the truth and then turned away from it at the last step and his story is almost unbearable. He tried a cunning plan. Rather than prove the fifth assumption directly, he would suppose it false and follow that supposition wherever it led, certain that it must eventually collide with some flat contradiction, some plain absurdity, and so prove itself impossible. He began deducing the consequences of a world in which the assumption failed, in which more than one parallel could pass through a point, and out came theorem after theorem, strange, unfamiliar, but each one following cleanly from the last with never a contradiction in sight. He built, without realizing it, a complete and consistent new geometry. But he had staked everything on finding it absurd, and so, when the results grew strange enough, he declared them repugnant to the nature of the straight line, called that revulsion his contradiction, and published his book proudly announcing that Euclid was cleared of every fault. He had held the greatest discovery in the history of geometry in his own hands, written it out page by page, and mistaken it for a monster because it did not look like home. He could not see that strangeness is not contradiction, that a geometry can be utterly unlike the one we know and still be flawlessly logical, still be true to itself. That final act of courage, to look at the strange new geometry and see not a monster, but a world, fell, almost at the same moment, and in 3 separate places, to 3 men who did not know what the others were doing. And the truth they each grasped was this: the fifth assumption cannot be proven from the rest, and it cannot be proven because it is not a consequence of them at all. It is a choice. Accept it, and you have Euclid's familiar geometry, the geometry of the flat page. Reject it, replace it with something else, and you get other geometries, strange, but every bit as consistent, every bit as valid. For 2,000 years humanity had believed Euclid's was the one true account of space, as necessary as logic itself. It turned out to be merely one option among several, and beyond it lay whole other worlds of shape, just as real to reason, that no one had dared to enter. The greatest of the 3 was a German, Carl Friedrich Gauss, called by many the finest mathematician who has ever lived. His gifts showed absurdly early. There is a famous story of him as a small boy in school, told with the other children to add up all the whole numbers from 1 to 100 as busy work, and returning the answer almost at once, because he had seen that the numbers could be folded into 50 pairs, each summing to 101. As a young man, he made a discovery so dear to him that it set the whole course of his life. He found that a regular figure of 17 equal sides, a shape the Greeks had wanted and failed to build, can, after all, be constructed with nothing but straightedge and compass, and he worked out exactly which regular figures can and cannot be so built, closing a question that had stood open since antiquity. He was so proud of the 17-sided figure that he asked for one to be carved on his gravestone. And here is a thread that ties his abstract genius to the solid earth. Gauss spent years of his life on the unglamorous public work of surveying, mapping the kingdom of Hanover, hauling instruments across the countryside, and he even measured the angles of an enormous triangle stretched between 3 mountain peaks, in part to test whether the angles of a truly vast triangle would add up to what flat geometry demands, or whether space itself might be subtly curved. The prince of pure mathematics, out in the fields with a measuring tent, asking the ground itself whether Euclid was right. For Gauss had understood, by around the time he was in his 20s, the very thing Zachary had fled from, that a consistent geometry could be built by denying the fifth assumption. He worked much of it out privately, and then he did something that tells you as much about his age as about him. He hid it. He locked the discovery in his desk and told almost no one for decades. Why? Out of fear of the uproar. The reigning philosophy of his day insisted that Euclid's geometry was a necessary truth, the only possible shape a human mind could give to space, and to deny it publicly sounded like madness or heresy. Gauss, respected and cautious, dreaded what he called the outcry of the dull, and chose silence over scandal. He buried one of the great discoveries in the history of thought rather than face the ridicule of small minds, and this silence set the stage for a heartbreak. Gauss had an old friend, a Hungarian named Farkas Bolyai, who had wrestled with the fifth assumption for years and come to loathe it. Phorcys had a son, Janos, a brilliant, fiery young army officer, mathematician, violinist, and swordsman, and the son caught the same obsession. The father, who knew its torments, begged him in an anguished letter to give it up, to fear it like a passion that could rob him of his peace and his happiness and all the joy of his life. The son would not listen, and the son succeeded. On his own, in his early 20s, Janos Bolyai grasped the same new geometry, and unlike the guarded Gauss, he was electric with the joy of it. He wrote to his father a line that has echoed through science ever since, that out of nothing he had created a strange new universe. His father, proud, arranged to print the young man's work as a short appendix to a book of his own, and then sent it to his famous old friend Gauss, hoping for a blessing that would crown the boy's career. Gauss's reply crushed Nos. He wrote that he could not praise the work, because to praise it would be to praise himself, for it agreed almost exactly with meditations that had occupied his own mind for 35 years. He meant it as a strange compliment. It landed as a death blow. The young man, who thought he had made a whole new universe out of nothing, learned that the greatest authority alive had quietly been there before him. His triumph turned to ash. He came to suspect Gauss of trying to steal his glory, sank into bitterness, published almost nothing more, and died decades later in obscurity, leaving mountains of unread manuscripts behind. He had done something immortal, and it broke him. And there was a third man, working utterly alone at a remote university out on the Russian steppe, Nikolai Lobachevsky, who reached the same new geometry independently and, unlike the others, had the nerve to publish it fully and first, years before Bolyai's appendix appeared. For his courage he was ignored and mocked by a mathematical world not ready to hear him, and he too died before his work was understood. Today we give the discovery to all three, and the strange geometry they opened is sometimes named for Lobachevsky, who dared to put it into print. 3 men, in 3 countries, strangers to one another, arriving at the same forbidden truth at nearly the same instant, after it had resisted the whole world for 2,000 years, not by luck, but because the time had come, and the idea was ripe, and it was only waiting for someone brave enough to reach. Now let me show you these other worlds, because they are far easier and lovelier to picture than their fearsome reputation suggests, and you do not need to leave your own house to find one. You are standing on it. Consider the surface of a sphere, an orange, a ball, the round earth beneath your bed. On a curved surface like this, what plays the role of a straight line? A true straight line is impossible, for you cannot draw one without leaving the surface. But the natural stand-in is the shortest path between 2 points that stays on the surface. And on a sphere, that shortest path is always an arc of a great circle, a circle as large as the sphere itself, one that cuts it into 2 equal halves. On the earth, the equator is such a circle, and so is every line of longitude running pole to pole. This is why an aeroplane crossing an ocean curves so far toward the pole instead of following the line that looks straight on a flat map. That northward arc, which seems a detour, is in truth the straightest and shortest road across the round world. And now watch the 5th assumption shatter. On the sphere, there are no parallel lines at all. None. Take any 2 great circles, any 2 of these straight lines of the sphere, and they always cross, twice, on opposite sides of the ball. 2 lines of longitude look perfectly parallel where they cross the equator, marching along side by side. And yet follow them, and they draw together and meet at the pole. On a sphere you simply cannot draw 2 straight lines that never meet. The very idea of parallel dissolves. And there is more. On the flat page, the 3 angles of any triangle add up to exactly half a turn. Always, that is one of the oldest certainties of school geometry. On the sphere it fails, and gloriously. Picture a triangle drawn on the earth. Start at the North Pole, run straight down to the equator. Turn a right angle and run a quarter of the way along the equator. Turn another right angle and run straight back up to the pole. You have drawn a triangle with 3 right angles in it, an impossibility on the flat page, yet plainly real on the globe, its angles bulging past the old limit. The larger the triangle, the more its angles swell beyond what Euclid allowed. And there is a mirror image to all this, the geometry the 3 lonely men actually discovered, which lives not on a ball but on a surface curved the opposite way, a saddle shape, curving up in one direction and down in the other, like a mountain pass or a potato crisp. On that surface, everything inverts. Through a point there run not one, but infinitely many lines that never meet a given line, and the angles of a triangle add up to less than half a turn, its sides drawn inward as if pinched. 3 geometries then, the flat, the spherical, the saddle, each internally perfect, each true to its own kind of space. Euclid's was never the one truth about space. It was the geometry of the flat sheet, one member of a family. Gauss drew from all this one more insight, and it may be the most profound of the whole night, because it changes what curvature even means. He proved a theorem he thought so beautiful he gave it a Latin name meaning the remarkable theorem, and its content is this: the curvature of a surface is something that lives entirely within the surface itself, detectable by a creature confined to it who could never rise up to look at it from outside. Imagine a tiny flat ant that can crawl on a surface but has no notion of any third dimension, no way to see the surface bending from above. Gauss showed that this ant could still discover whether its world was curved, and how much, purely by measuring within it, by drawing triangles and finding their angles swollen or pinched, by pacing out circles and finding their edges too long or too short for their width. Curvature is not something imposed from outside by how a sheet happens to be bent in space. It is woven into the intrinsic fabric of the surface, an inner property its inhabitants can measure without ever leaving home. This is why you cannot wrap a sphere smoothly in a flat sheet of paper without creasing or tearing it, and why you cannot flatten an orange peel without splitting it. The flat sheet and the sphere have different inner curvatures, and no bending can reconcile them. It is why every flat map of the round earth must lie. It cannot preserve all distances and shapes and areas at once, so every map you have ever seen distorts something, stretching the far north into monstrous size, or bending the straight into the curved, because a curved world cannot be honestly pressed flat. And this quiet, intimate idea that curvature is an inner truth a surface carries in itself, knowable from within, is the seed of the greatest revolution still to come tonight. For if a two-dimensional ant can measure the curvature of its world without stepping outside it, then perhaps we, living in 3 dimensions, might measure the curvature of our own space without any outside to step into, and perhaps space itself and time with it might be curved. That thought, planted here by Gauss, is the one a sickly young student of his would grow into a new geometry of any number of dimensions, and that a patent clerk in Switzerland would one day use to overthrow our understanding of gravity, the stars, and the shape of everything. That student was Bernhard Riemann, and he is one of the gentlest and most poignant figures in this whole history. He was shy to the point of suffering, sickly from childhood, painfully poor, deeply religious, and he would die of consumption at only 39, but inside that frail and timid man lived one of the most far-seeing minds mathematics has ever known. In 1854, still young and unknown, Riemann had to give a trial lecture to earn a position at the university, a kind of public examination before the faculty. As was the custom, he offered several possible topics, and Gauss, who sat among the examiners, chose the one on the foundations of geometry, the one Riemann had prepared least, and which touched the very questions that had haunted Gauss himself in secret for decades. Exhausted and anxious, Riemann pulled together in a few weeks a lecture that stands among the most important documents in the history of science. He wrote almost no formulas. He spoke in ideas, in pictures, almost in philosophy, and he swept geometry up into a generalization vaster than anything before. Where Gauss's remarkable theorem concerned the curvature of ordinary two-dimensional surfaces, Riemann conceived of curved spaces of any number of dimensions at all, 3, 4, more, spaces whose curvature could differ from point to point, bending one way here and another way there, gently in one region and fiercely in another. He built the mathematical language to describe any such space, however twisted, however many its dimensions, and to measure its curvature everywhere within it, from the inside, exactly as Gauss's ant measured its surface without stepping off it. It was an act of imagination so abstract that it seemed, in its own day, a beautiful irrelevance. What could anyone possibly want with the curvature of a 4-dimensional space that no one could see or visit? It looked like geometry dreaming with its eyes open, art for art's sake, with no conceivable use in the solid world. Old Gauss, who rarely praised anyone, is said to have walked home from that lecture shaken by the depth of what his student had glimpsed, and then Riemann coughed his way to an early grave, never dreaming that his useless dream of curved higher-dimensional space would become, half a century on, the very scaffolding of physical reality. The man who reached for it was Albert Einstein, and the problem that drove him was the oldest and most familiar force there is: gravity. Newton had described gravity with magnificent precision as a force reaching invisibly across empty space, each body pulling every other. But Newton himself confessed he could not say what the force was, or how it crossed the void, how the sun could grip the distant earth across 100 million miles of nothing without any thread between them. Einstein's answer, one of the most beautiful ideas ever conceived, was to abolish the force entirely. Gravity, he proposed, is not a force at all. Gravity is the shape of space. He suggested that space and time are joined into a single flexible fabric, space-time, and that this fabric is not a rigid, flat stage on which events play out as everyone had assumed, but something bendable, which any mass warps and curves around itself, the way a heavy ball set on a taut sheet sinks and dimples the cloth. And other objects, moving through that warped fabric, simply follow the straightest paths available to them within the curvature, those shortest, straightest lines that Riemann's mathematics knew how to describe on any curved space. The earth does not circle the sun because a mysterious force tugs it. It circles the sun because the sun's great mass curves the space-time around it, and the earth is only rolling along the straightest track that curved valley allows. The apple does not fall because the earth reaches up and pulls it. It falls because the earth's mass has bent the very space around it. And the apple is following that bent space downward. Gravity, the weight of your own body pressing gently into the bed at this moment, is not a pull. It is geometry. It is the humble craft of the rope stretchers on the Nile, raised at last to describe the architecture of the cosmos. And to write this theory down, this vision of a space-time curved by mass, Einstein needed exactly the mathematics of curved spaces of many dimensions that a dying young man had dreamed up half a century earlier for no reason but its beauty. Riemann's geometry, that seeming irrelevance locked away in the libraries, turned out to be the precise and only language in which general relativity could be spoken. Without it, Einstein could not have written a word. The tool had been forged and left waiting in the dark for 50 years, until physics came at last to claim it, the deepest proof our night has yet offered of that recurring miracle, that mathematics pursued for pure love with no thought of use becomes the key the universe was quietly waiting to be unlocked with. This was not left as a lovely notion, either. Einstein's idea made a hard prediction. If mass bends space, then even light, passing close to a very massive body, must swerve as it follows the curved fabric. Starlight grazing the sun should be bent slightly from its path. The trouble is that the sun's blaze normally hides any star near it. But during a total eclipse, when the moon blots out the sun and the sky goes dark, those stars leap into view. So, a few years after Einstein published, expeditions sailed to remote places to photograph the stars around an eclipsed sun and measure whether their light had bent by precisely the amount he foretold. It had. The starlight had swerved exactly as the curved space theory demanded, and overnight Einstein became the most famous scientist on Earth. The universe itself had confirmed that a shy consumptive's abstract dream of curved higher space was the true shape of reality. Once you accept that space can curve, an old question becomes suddenly answerable, a question that would once have sounded like nonsense. What is the shape of the entire universe? Is the cosmos as a whole flat, like Euclid's endless page? Or does it curve around like the surface of some unimaginable sphere, closed and finite, so that a traveler going forever straight would circle back to the start? Or does it curve the other way, like an endless saddle? This is no longer idle metaphysics, it is something we can measure. By studying the most ancient light in existence, the faint afterglow left over from the birth of the universe, still washing over us from every direction, astronomers have gauged the geometry of the cosmos at the largest scales, and the answer, so far as we can tell, is that the universe is very nearly flat. On the grandest scale, after this whole long journey away from Euclid and into stranger worlds, our universe turns out to look remarkably like the flat geometry of the ancient Greeks after all, which is either a joke or a mercy, depending on your mood. And yet flatness overall does not mean flatness everywhere. Around every star and planet, and above all around the crushed and monstrous objects we call black holes, space dimples and bends and plunges, a black hole is a place where so much mass is packed so tightly that the curvature of space-time runs away to an extreme, folding so steeply that not even light, following the bent fabric, can climb back out. It is the point where the gentle geometry of Gauss and Riemann reaches its most violent expression, where the shape of space curls up almost past imagining, and the rules that hold in the flat calm of your bedroom break down entirely. The cosmos, it turns out, is a vast and nearly level plain, dented everywhere with wells wherever matter gathers, and pierced here and there by bottomless pits where the geometry falls forever inward. Now, alongside this great current of curvature, running through the very same 19th century, another deep transformation was reshaping geometry from a completely different direction. A revolution not about the bending of space, but about symmetry, about what stays the same when everything else moves. And its story begins with one of the most tragic and romantic figures in all of science, a French youth named Évariste Galois. Galois was a mathematical prodigy of ferocious originality and equally ferocious temper, a passionate republican in a turbulent age. Twice rejected from the school he wanted, his work repeatedly lost or dismissed by the great men he sent it to, and at the age of 20 he was drawn into a duel over politics or a love affair or both. The truth is murky, and, convinced he would die, he spent the last desperate night of his life scrawling out his mathematical ideas by candlelight, scribbling in the margins that he had no more time. No more time. The next morning he was shot, and he died at 20, and it took the world decades to understand that the frantic notes of that final night contained one of the most important ideas in the history of mathematics. Galois had invented, in essence, the mathematics of symmetry itself, a way of capturing, with perfect precision, all the ways a thing can be transformed while somehow remaining the same. Mathematicians call the resulting structure a group, and it is one of the master keys of the modern subject. Let me give you the feel of it, because it is simpler than it sounds, and it is everywhere. Take a square, and ask, in how many ways can you pick it up, move it, and set it down again so that it looks exactly as it did before? You can turn it a quarter turn, or a half, or 3/4, or leave it be. You can flip it over across any of several lines. Collect together all those motions that leave the square looking unchanged, and you have captured the symmetry of the square, made into a definite mathematical object you can study and compare. Every shape, every pattern, every structure has such a collection of symmetries, the motions that leave it looking the same, and Galois's insight was that this collection, this group, is itself a thing of deep and rigid structure, and that understanding it unlocks the object. This is the idea that finally answered those 3 ancient impossible constructions I first raised long ago: squaring the circle, doubling the cube, trisecting the angle. Their impossibility was proven, at last, not by geometry but by this new mathematics of symmetry and number descended from Galois and his contemporaries, which showed exactly which lengths a straightedge and compass can and cannot construct, and placed the answers to those problems forever outside that reach. The oldest questions in geometry were closed by the youngest branch of mathematics, invented in part by a boy the night before he died, and a mathematician named Felix Klein saw how to turn this idea of symmetry into a lens that brought the whole sprawling subject of geometry into a single focus. By his time, geometry had splintered alarmingly. There was Euclid's geometry, and the strange non-Euclidean geometries of the sphere and the saddle, and the projective geometry of shadows and vanishing points, and more besides, and no one was sure how they all fit together, or whether they even belonged to the same subject. Klein's unifying stroke, announced in a famous program, was to say that every geometry is simply the study of whatever stays unchanged under some particular group of allowed motions. Choose your group of transformations, the motions you are permitted to make, and the geometry is nothing but the collection of properties those motions leave alone. In ordinary Euclidean geometry, the allowed motions are the ones that preserve distances and angles, sliding, turning, reflecting, and so lengths and angles are the things worth studying. In projective geometry, the geometry of the painter's shadow, the allowed motions are the far freer transformations of projection, which crumple distances and angles beyond recognition but leave certain deeper relationships intact, and so those are what that geometry studies. Each geometry, Klein saw, is defined entirely by its symmetries, by what it lets you do and what stays fixed while you do it. At a single stroke, the whole quarrelsome family of geometries fell into order, revealed as siblings, each one the study of a different notion of sameness. This is also the moment to settle a plant I left you long ago. In the Islamic halls of tessellated tile, the question of exactly how many fundamentally different ways a pattern can repeat across a flat surface is a question about symmetry groups, and its precise answer, that there are exactly 17 such families of repeating pattern, no more and no fewer, is a jewel of this same science of symmetry, a fact those medieval craftsmen felt their way toward by eye and hand centuries before anyone could prove it. Symmetry, which had seemed a matter of mere prettiness, turned out to be the hidden principle organizing all of geometry, and much of physics besides, for the deepest laws of nature we now know are themselves statements about what stays the same when the world is transformed, direct descendants of the ideas a doomed young man set down in his final hours. Riemann had done something else when he threw open the door to spaces of any number of dimensions. He had licensed the human mind to think about a fourth dimension of space, and once mathematicians had that permission, they could not resist trying to picture it, even knowing they never truly could. We live in 3 dimensions of space. We can move up and down, left and right, forward and back, and that seems to exhaust the directions there are. But is there some fourth direction, at right angles to all 3 of those at once, into which one might move, if only one knew how? Mathematically, there is no difficulty at all. The geometry of 4 dimensions is as consistent and well-behaved as any other, and mathematicians work in it, and in 5, and in 1,000, as comfortably as in 3. The difficulty is only in the seeing, for we are prisoners of the 3 dimensions we were born into. There is a beautiful way to feel the shape of this problem, given to the world in a small, strange book written more than a century ago about an imaginary country called Flatland, a world of only 2 dimensions, a perfectly flat plane inhabited by living figures, triangles, squares, circles, who slide about upon their surface and cannot conceive of up or down, for whom the very idea of a third direction is unthinkable nonsense. Now imagine a 3-dimensional being, a sphere, passing slowly through that flat world. The flat creatures cannot see the sphere itself, they can only perceive the slice of it that lies in their plane at each instant. As the sphere passes through, they would see a point appear from nowhere, swell into a small circle, grow to a great circle, shrink back down, and vanish. A thing appearing out of empty space, changing size by magic, and disappearing again, utterly baffling to them, though to us, watching from above, it is simply a ball dipping through a sheet. And the book's quiet, vertiginous suggestion is that we might stand in exactly the same relation to a 4th dimension we cannot see. A 4-dimensional object passing through our space would appear to us as something materializing from nowhere, changing shape impossibly and winking out, and we, like the flat creatures, would have no way to picture the whole of it. We can reason about it, though, by climbing the ladder of dimensions. A point, with no size, swept in one direction, traces a line. A line, swept sideways, sweeps out a square. A square, lifted in the 3rd direction, sweeps out a cube. And a cube, pushed along that impossible 4th direction, would sweep out a 4-dimensional cube, a hypercube, a shape we cannot hold in our eyes, but whose properties we can count exactly, and whose flattened shadow cast down into 3 dimensions. We can build and turn in our hands, a cube within a cube, joined corner to corner. The nearest our world can come to a glimpse of a thing that does not fit in it. We cannot see the 4th dimension, but geometry lets us know it is there, and reason about it truly, and that itself is a kind of sight, the mind walking calmly into rooms the eye can never enter. And now let me bring us back down from those unimaginable heights to something you can hold in your hand or see out your window, because there was a strange and glaring gap in all the geometry we have traveled through tonight, and it took until our own age to fill it. Look at the shapes geometry had always studied: the line, the circle, the triangle, the sphere, the smooth curves of Apollonius, the perfect solids of Plato. They are all clean and smooth and regular. Now look at the actual world. A cloud is not a sphere. A mountain is not a cone. A coastline is not a curve you could draw with any compass. A tree is not a cylinder. A bolt of lightning is not a straight line. The branching of a river is not any figure Euclid ever named. The real forms of nature are rough, jagged, broken, irregular, endlessly crinkled, and for all its 2,000 years of glory, classical geometry had almost nothing to say about them. It was the geometry of an idealized world of smooth perfection that nature almost never troubles to obey. It was a mathematician named Benoit Mandelbrot in the second half of the last century who finally built a geometry for the roughness of the real world and gave it a name from the Latin for broken, the fractal. He noticed that the rough shapes of nature share a peculiar and haunting property he called self-similarity. Each small part resembles the whole. Break a little branch off a tree and it looks like a small tree. A jagged rock looks like a small mountain. And a coastline, viewed on a map of a whole country, shows bays and headlands, and if you zoom in on one small stretch, that stretch reveals its own smaller bays and headlands. And if you zoom in again, smaller ones still, roughness within roughness within roughness, at every scale, all the way down. From this Mandelbrot drew a paradox that sounds impossible and is perfectly true. How long is the coastline of an island? You would think it has some definite length, but the smaller the ruler you measure it with, the longer it gets, because a smaller ruler dips into all the little inlets a larger one skips over, and since there is detail at every scale forever, the measured length grows without limit as your ruler shrinks, climbing toward infinity. A coastline, in this strict sense, has no finite length at all. It encloses a finite patch of land with an edge of infinite intricacy. And these fractal shapes have a property stranger still. They can possess a dimension that is not a whole number. A line is one-dimensional, a surface 2, a solid 3, but a coast so crinkled that it begins to fill the plane without ever quite doing so has a dimension somewhere between 1 and 2. A fractional dimension, an object caught partway between a line and an area. You can build such things by a rule and watch the miracle happen. Take a simple triangle, and on the middle of each side raise a smaller triangle, and on the middle of each of those new sides raise a smaller one again, and go on forever. What you approach is a shape called a snowflake curve, whose boundary is infinitely long yet encloses only a finite area, an unending fence around a modest field. Or take a solid triangle, and cut a smaller triangle out of its middle, then cut smaller triangles from each piece that remains, on, and you approach a ghostly lace of a figure, riddled with holes at every scale, that is more than a set of lines, but somehow less than a solid area. And the most famous fractal of all is a shape born from the simplest imaginable rule applied over and over to numbers on a plane, a shape whose boundary, when drawn by a computer and magnified, reveals an infinite, unrepeatable garden of spirals and filaments and tiny copies of the whole, so that you may plunge into it forever, zooming in without end, and never reach the bottom. Never stop finding new and intricate country that no eye had ever seen before. It is a single mathematical object containing infinite detail, generated by a rule a child could follow, and it is genuinely, endlessly beautiful. And fractals are not a mere curiosity. They turned out to be nature's own preferred geometry. Your lungs are a fractal, branching and branching to pack an enormous surface for breathing into a small chest. The blood vessels threading through your body are fractal, reaching every cell by endless branching. Rivers and their tributaries, the forking of lightning, the crowns of trees, the edges of clouds, even the great web along which the galaxies are strung across the universe, all carry the fractal signature of roughness repeating at every scale. Geometry, which began among the smooth and perfect ideals of the Greeks, learned at last to describe the broken, crinkled, living surface of the actual world. There is one more country of geometry I want to walk you through before the night closes, and it is the strangest and the most playful of all. a place where the rigid old certainties of measurement melt away entirely. It is called topology, and it is sometimes described, half-jokingly, as rubber sheet geometry. For topology cares nothing at all for length, or angle, or size, or straightness, all the things ordinary geometry was built to measure. It asks only about the deepest, most stubborn features of a shape. The ones that survive even if you take the shape in your hands and stretch it, squash it, bend it, and twist it however you like, so long as you never tear it and never glue together parts that were apart. To a topologist, a ball of clay squeezed into a cube, or rolled into a sausage, or flattened into a plate is the same object throughout, because you can pass between these forms by pure stretching. And this leads to the field's most famous and delightful pronouncement that a coffee cup and a donut are, to a topologist, exactly the same shape. Look closely and you will see why. A donut is a lump with a single hole through it, and a coffee cup is a lump with a single hole through it too, the hole in its handle. Everything else about a cup, the hollow that holds the coffee, is a mere dimple that can be smoothed away by stretching, while the handle's hole can never be removed without tearing. Reshape a clay cup carefully, without tearing or gluing, and you really can turn it into a donut, the handle's hole becoming the donut's hole. What topology sees, and measurement misses, is that the essential fact about each is simply one hole. And so, to a topologist, the number of holes is a far more fundamental truth about a shape than any of its lengths or angles. A sphere with none, a donut with one, a figure-8 pretzel with two, and no amount of stretching can ever change that count. Topology grew from small, delightful puzzles into one of the deepest fields in mathematics, and its first seed was a walk. In the old city of Nigsburg, a river ran through the town, wrapping around 2 islands, and 7 bridges connected the islands to each other and to the banks. The townsfolk amused themselves on Sunday strolls with a question. Was it possible to walk through the city crossing every one of the 7 bridges exactly once, never doubling back over any? No one could manage it, but no one could say whether it was truly impossible or whether they simply hadn't found the trick. The great mathematician, Leonhard Euler, settled it, and in settling it invented a new way of thinking. He saw that for this problem the distances and shapes did not matter at all, only how things were connected. So he threw away the map and kept only the connections, shrinking each landmass to a dot and each bridge to a line joining 2 dots. And looking at that skeleton, he reasoned that any such walk was impossible here. By a simple and beautiful argument about how many bridges met at each place, since crossing into and back out of a region uses bridges in pairs, every landmass but your start and finish must have an even number of bridges, and in Nigsburg every landmass had an odd number, so the stroll could not be done, not by any cleverness, ever, in reducing a city to dots and lines. And caring only about connection, Euler had founded topology and the study of networks with it, the same mathematics that now underlies the internet, the map of every transit system, and the web of relationships in any crowd. Euler left topology another gift, a formula so simple and so surprising that it feels almost magical. Take any of the perfect solids, or indeed almost any solid figure with flat faces, count its corners, count its edges, and count its faces. Euler found that if you take the number of corners, subtract the number of edges, and add the number of faces, you always get exactly 2. For the cube, 8 corners, 12 edges, 6 faces, 8 minus 12 plus 6 is 2. For the tetrahedron, the same. For any of them, and for endless lumpy shapes besides, always 2. It is a hidden law knitting together the parts of any simple solid, blind to all their sizes and angles. And here's the wonder, that number 2 is really a signature of the shape having no holes, of its being, topologically, a sphere. Do the same counting on a shape with a donut's hole through it, and you get not 2, but 0. The little sum sees straight through all the surface detail to the deepest fact of all, how many holes the thing has. A humble tally of corners and edges and faces turns out to be reading the soul of the shape. Topology holds objects stranger than any we have met, objects that overturn what you thought you knew about the very idea of a surface having 2 sides. Take a long strip of paper, and instead of joining its ends into a simple loop, Give one end a half twist before you join them. You have made a band with a single astonishing property. It has only one side. Run your finger along it, and without ever lifting off or crossing an edge, you will travel what seem to be both surfaces and arrive back where you began. The inside and the outside are one continuous face, and an ant could walk the whole of it and never once cross over a rim. It has, likewise, only a single edge, one continuous rim winding around. And if you take scissors and cut it down the middle all the way around, it does not fall into two loops as you would swear it must, but opens into a single, longer loop, still linked with itself in a way that defies the hand until you try it. It is a small miracle you can make in 10 seconds with paper and a twist, a first taste of how strange surfaces can be. And there is a stranger sibling still, a shape called a bottle after the mathematician who dreamed it up, which is to this one-sided band what a full closed vessel is to a mere ribbon. A surface with no inside and no outside at all, where the inner face flows seamlessly into the outer with no boundary between them, so that a fly could walk from what looks like within to what looks like without ever crossing a rim or passing through the wall. The catch is that such a thing cannot truly be built in our three-dimensional world without passing through itself. It can only exist honestly, without self-collision, in 4 dimensions, that same 4th dimension we could reason about but never see. The models of it you may have seen in glass, where the neck plunges through the side to join the base, are shadows of the true object, which lives cleanly only in a space with one more dimension than ours. And topology holds the deepest riddle our night will touch and one of the most human stories in modern mathematics, so let me close this final country there. If you were a creature living inside some space, unable to step outside it, how could you tell what shape your whole universe was, whether it was, in the deepest sense, a sphere, or something with holes, or something stranger? For surfaces, for 2-dimensional worlds, this had long been understood. But for 3-dimensional spaces, the kind we might actually inhabit, a single haunting question stood open for 100 years. It amounts to asking whether a certain simple test, a test you could in principle perform from within, using loops of thread to feel out whether every loop in your space can be drawn tight to a point, is enough to guarantee that your space is essentially a sphere and nothing more twisted. It sounds almost childishly simple. It was one of the hardest problems in all of mathematics, unsolved for a century, one of a handful for which a great prize of $1 million was offered. And it was finally cracked at the turn of this century by a reclusive Russian mathematician named Grigory Perelman, who posted his revolutionary solution quietly on the internet rather than in any journal. Let the world's experts spend years confirming that he was right, and then, when they offered him the $1 million prize and the highest medal in mathematics, refused them both. He wanted no money, no medal, no fame. He withdrew from mathematics and from public life almost entirely, saying in effect that the beauty of the proof was reward enough and that the prizes were beside the point. There is something fitting, something that closes a great circle, in ending our long night here with a man who solved one of the deepest problems about the shape of space itself, and then walked away from every reward the world could offer, because the truth alone was what he had wanted. He is, in his strange and solitary way, the last heir of that old man in the sand at Syracuse, who also valued the shape he had found above everything the world outside was shouting. Before we let all of this go soft and drift toward sleep, let me set a few last small wonders in front of you, gently, one at a time, like stones laid out on a windowsill, new marvels, each complete in itself, nothing you need to connect or keep. Here is the first. We spoke of the strange saddle-shaped geometry where triangles grow thin and infinitely many lines can miss a given line, and I told you it was hard to picture whole, because no perfect example of it sits in our ordinary world. But an artist found a way to show it to the eye, the same Dutch artist, enchanted by the tiled walls of Spain, who had made a life of drawing patterns that lock together and creatures that melt one into another. Late in his life he learned, from a mathematician, of a way to draw that impossible curved geometry inside an ordinary flat disk by letting the shapes shrink smaller and smaller as they approach the rim, so that an infinite world is pressed into a finite circle. its edge crowded with endlessly diminishing figures that never quite arrive. He made from this a series of prints in which angels and devils, or fish, tile a round disk, each one the same size as every other in the strange inner geometry of that world, though to our outside eyes they appear to dwindle to nothing as they near the boundary. He had rendered the infinite and the non-Euclidean visible on a sheet of paper, a whole boundless universe of shape, caught and held inside a circle you could cover with your hand. It is one of the most beautiful meetings of art and mathematics there has ever been, a hyperbolic world made gentle enough to hang on a wall. Here's the second, and it is a thing you have blown into the air as a child and watched drift and burst. A soap bubble is a small master of geometry, and it solves, instantly and without thought, a problem that is genuinely hard. Given a certain amount of air to enclose, what shape wraps it in the least possible skin? The bubble answers with a sphere, always, because the sphere is the shape that holds the most volume inside the least surface, nature's own economy, the roundness of the bubble a direct expression of it, the film pulling itself taut into the tightest, thriftiest form there is. And stretch a loop of wire into any twisted shape you like, of any wild outline, and dip it into soapy water. And the film that spans it will pull itself into a surface of the smallest possible area that can hang on that frame, a shape mathematicians call minimal and struggled for centuries to describe with equations, while the soap film finds it in an instant, effortlessly, by the plain physics of a skin drawing itself as tight as it can. Where two bubbles meet and merge, they even join their walls at precise and unvarying angles, the same everywhere, as if obeying a law they were taught, which, in a sense, they were, by the geometry of least surface written into the pull of the film. There is a whole hidden mathematics of these minimal surfaces, elaborate and deep, and a child at a summer fair commands it perfectly without knowing a word of it. Here is the third. Take a piece of string, tangle it loosely, and join its ends into a closed loop. You have tied a knot, or perhaps you have not, for the tangle may fall straight when you pull it, or it may be a true knot that no pulling will ever undo without cutting. And this simple, homely thing, the knot, turns out to hide a rich and difficult geometry, a whole branch of topology devoted to it. For the deep question is startlingly hard, given two tangled loops. Are they truly the same knot in disguise, one able to be rearranged into the other without cutting, or are they genuinely different? Your hands cannot always tell. A knot can be jumbled into 100 unfamiliar shapes. Mathematicians have spent more than a century inventing clever ways to fingerprint a knot, to compute from its tangle some quantity that never changes however you rearrange it, so that if two loops give different fingerprints, they cannot possibly be the same knot. It is subtle, unfinished work, beautiful in its difficulty, and it is not idle. The long molecules of life inside your cells, the threads of your own genetic code, can become knotted and tangled as they coil, and living things carry special machinery to cut and rejoin and untie them, so that the mathematics of knots, dreamed up by people playing with loops of string, turns out to describe a matter of life and death happening inside every cell of your body as you lie here. And here is the last wonder, which reaches back to those stacked oranges and forward into dimensions we cannot see. We spoke of the puzzle of packing spheres as tightly as possible in ordinary space, and how it took 4 centuries to prove that the greengrocer's humble pile is the best that can be done. But mathematicians, once they had spaces of any number of dimensions to play in, asked the same question there: what is the tightest way to pack the round balls of 4-dimensional space? Or 8, or more? Spheres we cannot picture nestled in rooms we cannot enter? For most dimensions the answer remains unknown to this day, a wilderness of open questions. But in a few particular dimensions, something magical happens. In the 8th dimension, and again in the 24th, there exist packings of a perfection and symmetry so exquisite, so obviously right, that the balls lock together in a single flawless crystalline pattern of astonishing beauty. And only a few years ago, in our own time, a young mathematician, working through a pregnancy and the ordinary press of a life, found the argument that finally proved these particular arrangements are truly the best possible, closing a question in those high strange dimensions that no one had been able to settle, one of the loveliest results of recent mathematics, and a reminder that this ancient science is not finished, not remotely, but is being carried forward still, this very year, by living people reaching into spaces the mind can barely hold. The story that began with a knotted rope in the mud is still being written, tonight, by hands you will never see. We have come a very long way tonight, further than almost any journey the mind can take. From a wet knotted rope pulled taut across the mud of a flooding river, to the curvature of space and time, to surfaces that live only in dimensions we cannot see. And I will not walk you back through it all, you do not need it, and you may already be halfway into sleep, which is exactly where you should be. Let me leave you instead with only the shape of the whole thing. The single arc beneath all the names and centuries. Geometry began as the most earthbound craft there is, the measuring out of fields so that farmers would not come to blows, the squaring of corners so that walls would stand. It was mud and rope and the patient redrawing of boundaries the river kept dissolving, and from that most practical of beginnings it rose and rose and rose into proof, into the perfect solids, into curves cut from cones for no reason but their elegance, into the fusion of shape and number, into geometries no one had believed could exist, into the curvature of the cosmos and the counting of holes in space, until the humble art of measuring the earth had become the language in which the universe writes its deepest laws. And at nearly every turning, the thing that carried it upward was not usefulness but beauty. Again and again someone chased a shape or a proof for no reason but the pleasure of it, with no thought of any use. The curves of a cone, the curvature of an abstract higher space, the symmetries of a doomed young man's final night, and again, generations later, that useless beauty turned out to be the exact key some corner of reality had been waiting to be opened with. It is as though the universe were built, at the deepest level, out of the same beauty the mind delights in for its own sake, so that to follow that delight far enough is, somehow, to end up reading the blueprints of the world. So let that be the thought you carry down into sleep, gently, with nothing to hold and nothing to keep. You are lying tonight inside geometry, wrapped in it, made of it. It is in the faint curve of space bending around the mass of the earth beneath you, which is the whole of what gravity is. It is in the branching fractal of the vessels carrying warmth through your body as you rest, and in the branching of the trees breathing quietly outside your window. It is in the roundness of the moon if it is up, and in the straight true corners of the walls around you, direct descendants of a knotted rope on a riverbank 4,000 years gone. The hidden order is everywhere, patient and silent and exact, holding the world in its quiet frame whether anyone thinks of it or not. And for 4,000 years a long chain of curious souls, farmers and priests, sages and prisoners, dreamers who died young and geniuses who walked away from every prize, gave their lives, a little at a time, to reading that silent order. Now there is nothing left for you to do but let it all go soft and dim, and rest. Let the ropes and the rivers, the cones and the curves, the spheres and the vanishing points drift apart and fade. Let your breathing slow, and let yourself sink, without effort, into sleep, held all the while in the oldest and gentlest of all the sciences, the quiet, perfect, unending order of geometry. Good night.